So we will continue now with the second talk. First we will have the continuation, and after that we will have the other talk is images of a special function under FC, fractional calculus operators, well predictable results.
Yes. So as I mentioned, I like just to continue with some few examples recently studied, say Maynard and Messina, and then Paris extended this case to consider the so-called complementary exponential integral, where they changed the exponential function by the Mittag-Leffler function first with one parameters, and Paris did this for two parameters. Here is missing the gamma. So you have power series gamma of alpha k plus 1 and the other gamma, two gamma functions. For beta equal to 1, it is the case considered by Maynard and Mosinov. They make some numerical plots for this function, some applications, and Paris extended this to the case with arbitrary alpha and beta. You see here the definition. Two gammas in the numerator, two gammas in the denominator, and it is practically right function psi with p and q equal to 2. Paris studied symptotic expansions. Maynard and Messina provided some numerical plots, and so on. And just few words I told you maybe yet on Monday, to be careful with so-called new special functions that are based on gamma k, which is a variation of the classical gamma functions. So all the objects they define by means of this gamma k function are easily reducible by this relation to the classical cases of fractional calculus operators, of special functions that are defined by means of this, and so on. So these are not new, but you see many papers I put the references of this my survey paper. How many authors published and published and published works on these so-called new special functions, like this in 29. You can, as an exercise, check with this case how can be reduced to F01 function, just Bessel function, nothing new. But they solve some K-Bessel differential equations. They find some images of the fractional calculus operators, like I will mention in the next talk, and so on and so on, which is not new at all. And here are many other examples you see in equation 30. Again, it can be presented like right function, and then the theory of the right function. You see how many other indices involved in so-called new special functions. But I always show that these are non-special functions. So maybe, and also there is S function. I will mention also in the next talk. Again, by some similar variations of parameters given, but based on the K analogs. This is an interesting class of so-called M and K series. Just because these are combinations, you see, of the idea of the PFQ function, this part, and the Mittag-Leffler functions in this part. So it is like a combination between generalized hypergeometric function and Mittag-Leffler function. and they do some theory, but it is always can be presented as a psi function in right sense. So all the theory, and well, I continue. Because you can ask me, what about numerical algorithms I expect for all these functions I mentioned? I'm not at all expert in numerical methods, but in the survey paper on this guide to special functions and the last section, I provided some information I got from my colleagues in fractional calculus. Well, first was Marichev, who of course developed Wolfram softwares for some of these functions, but only in special cases. Also, Mainardi, Podlubny, Garapa, Luchko, but you need in mind that it is only for few classes, the Metakleffer function classical, the classical right function, and only in such few cases. In the general case, still are not numerical algorithms developed for special functions of fractional calculus. Well, so now I go to, okay, so to the slides of the next talk. It is just analytical continuation of the previous information and based on same kind of works in the book, my survey papers in the journal House Solitons and Fractals with the title Fractional Calculus Operators of Special Functions. The result is well predictable. We see why. And next, in American Institute of Physics conference proceedings, in Frontier Physics as a critical paper, and also this next ones in the handbooks of fractional calculus with application volume 1, two papers, one by myself and one joined with Luchko, and survey paper in mathematics in 2020. So, what is about the evaluation of images of special functions and some operators of fractional calculus? It is become very hot topics as topic of dozens, but maybe now 100 papers by different authors that find places in comparatively good journals. They are published, but they ignore that all this is known. It can be easily done in just in few lines to know what is the image. Practically, the images, evaluating of images of fractional calculus, integrals, or derivatives is somewhat to evaluate some improper integrals because the functions inside have singularities in the limits of integration. Say of products of two special functions or one elementary, one special function, and it is to find the fractional derivative. Then after that you can need to take additional differentiation of this. And finally to go to some other special function that either can be known or just written in some complicated series and nothing more. So some examples you see if you like to have this Erdős-Cooper integral of exponential function. The solution, the result is right function with p and q equal to 1. When you have inside Bessel or generalized Bessel function, the result is 1 psi 2. If it is derivative, you can once again differentiate this, and so on. Uh, what can be used to do this? The standard techniques that are used in this many papers is to use the definition by power series, integrate them by the power series for the special function, then exchange order summation and integration, and interpret the new power series in the best case as some non-special function. But not always, because sometimes it looks complicated, then authors leave only this as power series and say this is the image. A general approach how to handle this problem was yet proposed by Marichev by using Milin transform techniques. I mentioned at first the book in Russian, then was later translated partly. The Russian book is Method of Evaluation of Integrals of Special Functions of 1978, and then it is partly translated as Handbook of Integral Transform of High Transcendental Functions, Theory and Algorithmic Tables. Well, I was dealing with this problem for many years, and yet the ideas of the approach I have given were in my very early papers, but recently I tried to republish or to make more condensed ideas in some survey papers, so to remind that the problem has very easy solution. Why? Because many of these items that are published are dealing with some operators of fractional calculus. And they use once Riemann-Liouville fractional integral, then the SIGO operator, Erdős-Kober operator, Marchev-Saigo-Moedo operators, and so on and so on. Then with special functions, you know how big variety of special functions we have in classical sense, in fractional calculus sense. When you change the special functions, you can produce other 100 variation and papers on this to say this is a variation of the image of such a function. But most of these functions are multi-index Mittag-Leffler functions, or right the generalized hypergeometric functions, and in the general case, Fox-H function. So all this can be done in one scheme, very easy to comprehend. I remember now, remind now the definition of the right generalized hypergeometric function, Pip's IQ, as it was in the previous talk, the Mittag-Leffler functions, the multi-index Mittag-Leffler functions, and from the first lecture on Monday, the definition of our generalized fractional integrals and derivatives that practically are single integrals using special functions like this h function in the kernel function. The integrals here from 0 to 1 has moved down. And in the simpler case, when all beta parameters are equal, this is represented by the g function, a little bit simple operators. And for this generalized fractional integral, we gave the definitions of the corresponding generalized fractional derivatives, where the auxiliary differential operator of integer order appears as polynomial of z, and then we can define Riemann-Liouville and Caputo type derivative. And we need just to remind few of the particular cases that when is equal to 1, these are the Erdős-Kober operators. The decomposition or composition result that same generalized fractional integrals can be represented as compositions of commutable Erdős-Kober derivative integrals or derivative in the classical sense, and this is very useful then used in evaluation of images of such operators. Then for m equal to 2 we have the hypergeometric fractional integrals, including the SIG operators which I'll mention. For m equal to 3 we have Marachev-Saigomet operators, also used in many papers in recent years as a topic to evaluate such kind of operators of some special functions. Well, we can start with some very known classical results, say for the PFQ function. Yet in Bateman, RD volumes on tables of integral transforms, also in ASCII lectures, notes on orthogonal polynomial and special functions. In a paper by Lavoie, Osler, Tremblay, and Syme review in 1976, one can find Riemann-Liouville integral of PFQ function in the general case, and it is shown that PFQ is transformed into same kind of function, but P and Q, the orders are increased by 1. It is very important result. And we use always in next in our approach. And some other examples were also known in literature. For example, the Poisson integral, written in this way, the cover operator of cosine function is Bessel function. Riemann-Liouville operator of exponential function gives one f1 function. Of the beta distribution gives Gauss function 2f1, and so on and so on. So these are classical results. But for our purposes, I put this in the form of all of them like RD-Kober operators with arbitrary three parameters for the delta of a general right function p psi q. And it is easy to follow like the classical results that the result always is the same kind of function where p and q are increased by 1. And of course, additional parameters in the function should appear. And corollaries of this are about the non-classical results. Same similar result is for RD-Kober fractional derivative. Again, p psi q goes into C with p plus 1, q plus 1. This is the basic result we use then, reminding them the generalized fractional integrals are compositions of classical RD-Kober operators. So we can make several steps. For example, one RD-Kober operator of p psi q, transform it in p plus 1, q plus 1 function. Then we apply the next RD-Kober operator, and p plus 1, q plus 1 are increased to p plus 2, q plus 2. And after m steps, the nth RD-Kober operator finally goes to psi function with order p plus m, q plus m. So the main result we explore in all this topic is that generalized fractional integral of p psi q function, where we'll also arbitrary such variable lambda and zeta to power mu and some additional multiply here. The general fractional integral is the same kind, exactly function, but p and q are increased by m. And always we know this, we can check if the result is true or incorrect, if some mistakes in evaluation. So for the simple case of PFQ functions, you see here, the result then is, of course, f function with p plus m, q plus m, of course. And similar result we have for generalized fractional derivatives. Well, we proceed with some examples. We go back to the classical results for Riemann-Liouville operators of special functions. Say this one, that Riemann-Liouville operator of p psi q function is p plus 1 q plus 1 psi function. And in many works of Kubers and some other co-authors, such kind of Riemann-Liouville integrals were evaluated in special cases, for example, of the Bessel function. But Bessel function is a 0 psi 1 function, and then Riemann-Liouville integral should just increase the p and q by 1, so we have the predictable result psi with 1 and 2 is p and q parameters, of course. Many other such similar papers are on images of generalized Bessel functions, and so on. All of them use the same reasons to get the result predictable. One can concentrate on the classical right function phi, which is the generalized Bessel function. Again, the result is well known. But people think that evaluations of so-called SIGO integrals are worth to make many new articles. What are the SIGO operators? You see here equation 31. This is operator introduced by SIGO in studying Euler-Darboux differential equations, also used in univariate function theory, but the very special and popular case of fractional calculus integral of hypergeometric type, because the kernel function includes the Gauss function. So we use this definition of the SIGO operator, but as mentioned, it is a case of our generalized fractional integral, so m is equal to 2. And then SIGO operators are just compositions of two Erdős-Kober classical integrals, for which we know how they act on special functions. So no need to make all this job. The compositions have had in the Erdős-Kober integrals of such special functions already. And the same they consider for SIGO fractional derivatives, of course. And again, some examples of works. For example, the SIGO operator of Bessel function was evaluated to be 2 psi 3 function. Naturally, because Bessel function is 0 psi 1, and you need to increase by 2 the indices p and q, and then you go 0 plus 2 is 2, and 1 plus 2 is 3. So we have this function we know in advance. Also, we put just for corollary some general result that SIGO operator p psi q function, which are almost all special functions, then the result is p plus 2 q plus 2 psi function. And for PFQ is the simple case. Also for the generalized fractional derivative in SIGO sense. Yet the more difficult and complicated case is considered as the so-called marriage of SIGO-MOED operators, in the titles often now also already abbreviated MSM operators. Marchev introduced such operator in studying some integral equations, And later Saigo and Maeda considered and introduced this separately as fractional calculus operator. You see the definition here. It depends on more parameters, and the kernel function is the f3 function, the so-called table f3 function or Horn function, which is defined by means of such power series in the unit disk for two variables z and c. But if you open the book by Prudnikov, Bychkov, Marichev, the third volume, you find that this f3 function is just a simple case of the Myers-G function with orders 3, 0, 3, 3. Remember that our kernels were in the general case GM 0 MM. That's on in this case m is equal to 3. So Marichev cycle operators are just case of the generalized fractional integrals of derivatives, and they are compositions of three classical Erdős-Koper operators. So we can make three steps, uh, and same for the derivatives. And to find the general result that Marichev-Saigo operator P psi Q function is the same kind of function where P and Q are just increased by 3, and this adds 3 additional terms in the parameters, of course, that depend on the indices of this operator. Some example of works on this. Kala and co-authors evaluated Marichev-Saigo operators of Bessel function. And as the Bessel function is 0 psi 1, its indices increased by 3 will give the predictable result as 3 psi 4 function. No need to do long evaluations. Here are just more examples of more complicated special functions from which authors have evaluated Marichev-Saigo model operators. But always such functions should be first reduced to right function, and then just apply the general result to increase the PQ indices, in this case by 3. We see here some generalized multi-index Mittag-Leffler functions studied by Agarwal, Rogozin, and Trujillo. These are practically 1 CM functions, and then MCM integrals should be, of course, presented like 4 CM plus 3 functions. Same for derivatives. Similar results are presented for various special functions. And I mentioned an interesting example at the M or K series, M series by Sharma, that are combination between PF function and Mittag-Leffler function. These are represented as P plus 1, Q plus 1 C functions, and then with all these very special cases, the result can be easily seen that Riemann-Liouville operator of such function will increase the indices, and then from PMQ function we go to P plus 1 MQ plus 1 function to be in advance known what to be expected. I mentioned that the multi-index Mittag-Leffler functions are kind of eigenfunctions of the Gelfand-Leontief integrals. First, we see a relation between Erdős-Koper operator taken of multi-index Mittag-Leffler function. Well, in this case, the index is beta are all increased by these duties, the component of the multi-order fractional integration. And then if we do for all indices applied, then we have that generalized fractional integral of multi-order delta k is the same kind multi-index Mittag-Leffler function where all the second parameters beta are increased by delta E, the orders of multi-integration, which is also well expected. I published some critical paper, especially one on these trials to evaluate images of special functions in frontier physics, because the authors claimed to evaluate fractional integral operators of generalized Lumel-Wright function. And the generalized Lumel-Wright function they consider is representable by psi function with P1 and Q equal to M plus 1. And all SIGO, Marichev-SIGO operators, Riemann-Liouville operators will have no result, just we increase this P and Q by 1, by 2, or by 3. And the result was correct, of course, in this paper, but written after very long evaluations. In advance, we knew that the result should be this kind of right generalized hypergeometric functions. Some of the authors were known, and the other evidently were some PhD where they have given this job to do, but they write after that some comments that show that they did not know the Samko-Kubas Marichev theory at all, so the comments were not adequate. Also, I'm mentioning this new kind of special functions with K analogs, S analogs, and so on. There is a paper of mine in American Institute of Physics conference proceedings of 1970 and then in 2019. Some examples. For example, if we take a function with K analog, K Bessel function, you see here, replace gamma K by gamma, and you get a typical psi function with P and Q 0 and 1, and you know what to expect after application of any kind of fractional calculus operator. So more complicated analogs are these. The approach works in same way. And I mentioned about these functions. You see the definition. Here we have part as the PF cofunction and as Prabhakar function gamma k, and the symbol, the Pochhammer symbol, but in terms of gamma k functions. Everything is reduced to the classical case of right generalized hypergeometric functions, say in this case to P plus 1, Q plus 1 psi function, and the results are known. Another case of multi-index right function with indexes k that are so I'd like to mention about more general result. If you cannot identify the special function as part of Mittag-Leffler functions or right functions, well, this function is generally a H function. But in all books on G and H functions, there is the Milin transform formula that gives a result like this, that integral of product of two arbitrary h functions is another h function. So in our case, we can use this very general formula so to give a result that any generalized fractional integrals in our sense, this one, of arbitrary h function is another h function with known in advance orders and parameters. And more simple case is when all beta parameters are equal, it's reduced to margin function. So the result for generalized fractional integral of a margin function is another margin function. Some conclusions on that part of the talk are the following. Instead of doing new experiments and exercises, first, if you like to evaluate the image of fractional calculus operators of a special functions, first you try to recognize the special function as a right generalized P psi q function or simply fq function, or in the more complicated case as Fox function or g function, and apply the results I mentioned. Then next step is to check if the operator of fractional calculus you like to evaluate is not among the special cases we mentioned, like Riemann-Liouville, Erdős, Kober-Saigo, Marichev-Saigo, Maeda, and any others that fall in the general fractional calculus cases, and then just apply the general results. And lastly, a little bit separate but related to all these results I mentioned is that using these tools of generalized fractional calculus and decomposition of the generalized fractional integral as products of Erdős-Kober, in general and classical fractional calculus operators, we can use to introduce new definition of the special functions, some special functions, and a kind of classification of the special functions in three basic classes. And why it is useful? Because for beginners, for applied scientists, all these details sometimes are too much, they don't need, but they say, oh, this is a special function of this class, similar to Bessel or similar to Gauss function. So it is expected that the behavior and the property should be similar, like very general view on this. Well, you know that special functions can be defined not only by the power series, but some other representation can be used. For example, for the Bessel functions, the Poisson integral mentioned by means of cosine also can be used to define the Bessel function. The Gauss function, which is defined only correctly by power series inside the unit disk, can have its extension outside by the Euler integral formula. And also this formula, like integral representation, can be used as definition. And well-known examples are the classical orthogonal polynomials. Most of them are usually defined by means of Rodriguez differential formulas, where you have some differentiation of some elementary functions that produce the classical orthogonal polynomials. And often these polynomials are defined by means of such Rodriguez type differential formula. So the same idea can be used for the special functions in general of fractional calculus, and also for classical special functions, again in the general case. In our works, even some rather older one, we have shown there is a paper in 1985, say, that the title is All the Classical Functions. Classical special functions are special integrals or derivatives of three kinds of elementary functions. So what we mean? And when I explain this, then we can classify the special functions in three such classes, basic classes, where we consider each of the special functions just to belong to one of the classes of special functions. Well, the idea is the following. Most of the special functions of fractional, classical or special functions of fractional calculus, as shown, are representable as PFQ or P psi Q functions. Then each P psi FQ function, or the right function of same kind, can be represented as Erdős-Kober integral of same kind of function where P and Q are reduced step by one. We apply a finite number of steps, like here, we always reach to some generalized hypergeometric functions with the lowest possible P and Q. For example, to function 1f1, which is the confluent hypergeometric function, or even 0f0, which is the exponent. To Gauss function, f with 2, 1, or even to the simple elementary function f with p 1 and q0, the beta distribution function. And for the Bessel kind of functions, when p is less than q, when difference is 1, it is the function we reach to it with 0 and 1. But in hyperbesel case, it could be here positive 0, f, and some positive index q minus p. But these are, so that these three cases, this one, and this one. And each special functions can be put in one of these three cases. So, depending on what, if p is less than q, if p is equal to q, or if p is equal to q plus 1. Of course, when p is greater than q plus 1, the power series for PFQ were not defined, then this was the reason Meyer and Mac-Robert and so on to introduce the more general G functions, for example. So, in the simple case, my proposition reads as follows, that all the generalized hypergeometric functions PFQ can be considered as generalized fractional integrals of generalized fractional derivative. Then I use the notion different integrals of one of the three elementary functions cosine for the q minus p plus 1. In the simple case is the classical cosine function is here is 2, to exponential function, or to this function which is usually also called beta distribution. And this theory is simple, but it is based on the classical results I mentioned in advance by Bateman, Erdős, Aske, Osler, Tremblay, and so on. And you should need only the generalized fractional integrals or compositions of classical fractional calculus operators. Then for the more general case of P psi q function, it is the same result, only the third function here is not the beta function but a little more specific special function 1 psi 0, but the same idea and the same results are repeated, yes. So, based on this, we can suggest the following classification of the classical special functions and also the special functions of fractional calculus. So, they to be either Bessel or cosine type, of congruent type, if P is equal to Q, or of Gauss or geometric type when P is equal to Q plus 1. And this can be just an easy view for beginners, applied scientists, engineers. Then don't try to avoid the deep knowledge on special functions, but just need to think of them as belonging to some classes similar to cosine and Bessel functions, to exponential functions, or to geometric series. So maybe, yes, it can be useful. And also it is useful to check if some results are correct, yes. So it was shortly to tell you about the ideas on special functions of fractional calculus and when we need to evaluate images of the special functions, that we can know the result what should be. Yes. Thank you.
Thank you, Professor
I
Kiryakova,
hope was
for
not so much in details to borrow the public because the results can be read in these survey papers, in other cited works by other authors.
no, it was in fact a very exhaustive historical about the fractional calculus. And well, we will put the slides on the
Okay.
website, so it will be available for anyone, even the open problems or about the geometrical interpretation, which is still open, but still a lot of things can be seen in the slides. Thank you very much again, and now we have lunch. We have. Oh yeah, one question. Yes.
So I'd like to get your opinion about the multi-variable cases.
Yeah.
We know that Luchko and
Luchko
Tomkin
is
introduced
case.
the multi-variable, and then in 2013 the Professor Kalla introduced
Yes,
the
also.
A12 variable, and that one we used in the representation of solution three terms.
Yeah, multi-terms in general.
Okay, but then at that paper he introduced a new one, E2, which has you can find in the denominator gamma function, there is a double series, and the argument of gamma function has a combination of this I and J.
Yes, like
so
maybe this Kilbas Rogozin, Saigos, or the similar.
Yeah, but can be happen that these multivariable cases also, like in one variable cases, can be like a
To be compared, yeah. Well, because there was some results presented to our journal that used the, say, two or multivariable definition of the solutions they found, but I see that the problems are, say, for hyperbessel operators where one variable is enough. So I asked the authors to try to compare it is some calculations, the coefficients of one representations and the other, at least in some special cases they should coincide. some of the authors succeeded to do some comparison. The other cases was difficult because using complicated coefficients, it's not easy to reduce one to the other, but in some cases it should be, because if the problem is the same, the solution should be given in equivalent forms. Yes, so maybe this partly answer this. There was a paper in last year, in this year, by two American authors, Dubovsky and we see they are cited, that they considered practically hyperbesel problems with fractional orders sometimes, and considered in details many special cases when what happens in the particular cases numerically and so on. And in some cases they should be conciseness. They try to do, but not always, yes. Well, we published the paper because it was interesting, but still this problem, I tried to say some 1-2 hours to calculate, but maybe did not, yes.
Okay, thank you.
So, any more question, comments?
So maybe also these inequalities, but one should say that estimate is also very important. If one wants to apply this to some problems, then having good estimates for these functions is not so.
They put some plots, some illustrative examples that partly should be given the connection, yes. But in the general case, to compare the coefficients of the representations was not so easy.
Even for some multivariate Clear function.
Yes,
Decay estimates.
to reduce to one variable case, but with more parameters, yes.
Yeah, and for the multidimensional case, we don't have the uniform estimate. We have some estimation on the some modes, but still, which is different from the two variables.
As more terms are in equations and more parameters, and more, as the case is going difficult and difficult, and the details are complicated, of course. Okay.
So, no more comments. Again, let us thank. Now we have sandwich. And